We'll be talking about rational functions and their graphs today in 3.5, and this is going to be part 1. So here's our objectives, and we'll do about half of them in this video and then the other half in the other one. And the main thing we're going to be talking about is these asymptotes here. So the definition of a rational function is that they are quotients of polynomial functions. So that means it can be written as a fraction. And the domain of a rational function is the set of all real numbers except the x values that make the denominator 0. So you've seen stuff like that before in previous lessons. So in this one, we want to know what is the domain of the rational function. So we know that the bottom cannot equal 0. So x minus 5 cannot equal 0. So if we add the 5 over, we get that x cannot equal positive 5. So the domain would consist of all real numbers except positive 5. And on the next slide, I'll show you how to write it in different notations. So set builder notation is the top one. X cannot equal 5. And then interval notation, you could go from negative infinity up to 5, but not including 5. That's why this is a parenthesis. And then 5 to infinity would also work. Just the number 5 itself cannot. Okay, if we look at this one, the bottom cannot equal 0. So let's set that equal to 0. Add the 25. X squared cannot equal 25. If you take the square root of that, you get x could not equal positive or negative 5. So the domain would be all real numbers except negative 5 or positive 5. So as set builder notation, we have this top one, x cannot equal negative 5 or positive 5. The domain, you could go from negative infinity up to negative 5. Then between negative 5 and positive 5 would work. And then 5 up to infinity. So it just can't be exactly 5. That's why we have parentheses or negative 5. If it was a bracket, it would mean you could include that number. Okay, now this one, if you see the math I do here, once I subtract the 25, you're going to get a negative. Now, if you do the square root of a negative, that's not going to give you a real number. You would get error because it's really the square root of 25 times the square root of negative 1. And this is an imaginary number, so that's where they get this plus or minus 5i. No real numbers cause the denominator to equal 0, so that means the domain could be any real number, from negative infinity up to positive infinity, because there's nothing here for a real number that I could put that will ever make the denominator equal 0. Okay, definition of a vertical asymptote. So the line x equals a is what we're going to be using, and that represents the vertical asymptote of the graph of a function. And you can see it increases without bound as x approaches a. So this function increases without bound. You can see the arrows as it approaches that vertical line. Same here, it's approaching the vertical line. It's going to keep increasing without end. So as x approaches this vertical line, a, f of x approaches infinity. And on this one, as x approaches this line, we're approaching infinity again. So that's just different visuals you can look at to help you understand what this vertical asymptote means. Okay, it also works if the function is decreasing without bounds. So this one, it's approaching that vertical asymptote there. So as it approaches that line, we're going to go farther to negative infinity. As this approaches that vertical line, we're also going into negative infinity. Okay, so now we need to figure out where can we find those, and it kind of tells you where the graph is going to start to curve, where it's going to just keep going but not past that line. So if this was the rational function and Px and Q of x have no common factors, and a is a 0 of Q of x, then x equals a is a vertical asymptote of the graph. So let's go ahead and figure out how to apply this. Find the vertical asymptotes, if any, of the graph. So sometimes there will not be any. So our first step is to factor the bottom to see if there are any common factors. So the bottom was x squared minus 9. That is the same as x plus 3 and x minus 3 because they're two perfect squares. So this can be rewritten as x plus 3 on the top over x plus 3 times x minus 3. And now we can simplify this. That leaves us with 1 over x minus 3. So the 0 of the denominator is what would make this equal 0, which would be positive 3. So if you add it over, you get x equals 3. So the 0 of the denominator is 3. That means the line x equals 3 is going to be a vertical asymptote for the graph. And this shows a visual of it. So the 0 of the denominator is 3, so that's where we get this green dotted line. And then you can see that the two curves are approaching that vertical line. Okay, if we try this one, let's go ahead and factor the bottom. We'd get x plus 1 times x minus 1. And the top is x. There are no common factors in the numerator and the denominator, so there's nothing we can simplify. So then we just need to find out what are these zeros. So what would make x plus 1 equal 0, and what would make x minus 1 equal 0? Well, that would be negative 1 and positive 1. So these are our two vertical asymptote lines. And here's where we see that. So yeah, this function definitely has a cool shape. It approaches the line, and then we have something in the middle where it approaches that line as well. So this is our x equals negative 1 line. This is our x equals positive 1 line. Okay, now this one, we cannot factor the denominator of h of x over the real numbers. So the denominator has no real zeros. There's nothing here that we could put in for x that would ever make the bottom equal 0. So it has no real zeros, so the graph has no vertical asymptotes. Okay, now we're going to look at horizontal ones. So now you can see it's going in the horizontal direction, and again it's the increasing or decreasing without bounds. So this one is increasing. This one is decreasing as it approaches. And this one also increases to follow that horizontal line. Okay, so we have this long rational function. You can see it's a fraction, it's saying this coefficient in front cannot equal 0 on the top or the bottom. Okay, the degree of the numerator is going to be represented by the n. So you can see that here, that's the exponent degree. And the degree of the denominator is the m. So the highest degree is at the front. So if the n is less than the m, the x-axis or the y equals 0 line is the horizontal asymptote of the graph. If n equals m, then the line y equals those coefficients divided by each other is the horizontal asymptote of the graph. If n is greater than m, the graph of f has no horizontal asymptotes. Okay, so let's find the horizontal one if there is one for this one. So the degree of the numerator is 2. The degree of the denominator is also 2, which is equal to each other. The leading coefficients of the numerator and the denominator are 9 and 3. So we get that from these numbers. So that's going to help us find our equation. And I'm getting that from our step 2, or option 2. If n equals m, then you have to find the quotient. So we get y equals the top divided by the bottom coefficient, which is y equals 3. And here's the graph of that. So y equals 3, you can see that it approaches. Now the picture makes it look like it goes a little above. It should not be going above. It's right below that blue line. It approaches that blue line. Okay, now this one, the degree of the numerator is just a 1, which is less than this 2 here. So the graph of g has the x-axis, and it does have a horizontal asymptote. So this is supposed to say is the horizontal asymptote there. So the x-axis is the same as y equals 0. And we got that from this. If n is less than m, the x-axis, which is also known as the y equals 0 line, is the horizontal asymptote. And there would be the graph of that. So this is the x-axis, which is the same as the line y equals 0. And you can see that this one approaches it, and then this one approaches it. Now this one, the degree of the numerator is greater than the denominator. So if n was greater than m, then there's going to be no horizontal asymptotes to this graph. And you can see that it's not going to be approaching any line together. They're kind of going off in their own directions. And we're going to end by talking about basic reciprocal functions. So this is the first one. 1 divided by x, the graph looks like this. 1 divided by x squared looks like this one. And our first one is an odd function. The symmetry is over the origin. And if n is less than m, then the x-axis or y equals 0 is going to be a horizontal asymptote. So on the top I have no degree, so it's a degree 0 on the top for n, and the m equals 1 on the bottom. So that is where I got n is less than m. And the other one is going to be an even function because it has y-axis symmetry. And then this one would also have a vertical asymptote at the x-axis because the top has a 0 degree and the bottom has a 2 degree. So n is less than m. Okay, so this is going to talk about transformations, which we have done in the past. So use the original graph that we learned, 1 divided by x. So that is this picture we have here. So we've identified 2 points the horizontal asymptote from the previous slide. And then the vertical asymptote is x equals 0, because the 0 of the denominator is going to be 0, because the bottom is just x, so x equals 0 would be the vertical one. So that's our green line, or sorry, our blue line, and then the green line is the horizontal one. And now we're going to try to figure out how can we transform it so it looks like this. So first we're going to look at what happens to the main part here. It's going to end up shifting 2 units to the left, because if you add 2 to the x, we've done ones like that before. If it was x plus 2, you had to go left 2. So you have to subtract 2 from each x coordinate. So our line was in the middle before, and now it went backwards to -2. So we shifted it backwards 2. And everything else is going to stay the same for now. We did move our black arrows, and they became the red arrows. We shifted the whole graph over. And now this -1 on the outside means we're going to go 1 unit down. So originally it was hitting that x-axis, now it's down here at -1. So we went down -1. So the red arrows are what you're looking at. That is your new graph. So the red graph is this one here. Okay, that's the end of that video. We'll continue this lesson in part 2.